Hello, let's talk about some of the properties of gases. You can't see gases, they're invisible, they're all around us, but we're interacting with them all the time. Every time you take a breath, you're interacting with some gas. And so the characteristics of gases. One is that a sample of gas assumes both the shape and the volume of the container that it's in, whereas a liquid will take the shape, but it won't fill up the entire volume. And a solid, of course, has a fixed shape and volume. Gases are compressible, can easily increase or decrease their volume, because you can't do that with liquids or solids. The density of gases are much smaller than those of liquids or solids, and the densities of gases depend upon the temperature and the pressure. And gases form homogeneous solutions with one another in any proportion. Those molecules that we'll learn momentarily are free to move about, and they can mix around very readily. So let's talk about the kinetic molecular theory of gases. The kinetic molecular theory explains how the molecular nature of gases gives rise to the macroscopic properties, the properties that you can see. There's some basic assumptions of the kinetic molecular theory. And the first assumption is that a gas is composed of particles that are separated by large distances. And the volume occupied by individual molecules is negligible. Large distances, infinitely small particles. These gas molecules are in constant random motion, and moving in straight paths, actually, until they collide with something. And that these collisions see no loss of energy. The term physicists use is that they collide with, the collisions are perfectly elastic. There's no loss of energy, exchange of energy from the gas molecules. And gas molecules do not exert attractive or repulsive forces on one another. That's what makes those collisions become truly elastic. These are our assumptions, so we're talking about give rise to the macroscopic properties of gases. And these we'll wind up calling ideal gases. And one other assumption that we have is that the average kinetic energy of gas molecules in a sample is proportional to the absolute temperature. The average kinetic energy, remember kinetic energy is the energy of motion, 1/2 mv squared, mass times velocity squared, is proportional to the absolute temperature. So as the temperature goes up, the average kinetic energy goes up, which means the average velocity is going up since the mass of a gas molecule is going to be constant. And whenever we're talking about temperatures in gases, we're always going to be referring to the absolute temperature on the Kelvin scale. That's really important. And so the average kinetic energy, that's what that E with a bar over it means, that bar means average, is directly proportional to the absolute temperature, capital T. So gases are compressible because molecules in the gas phase are separated by large distances. Assumption 1, that's how they become compressible. And the pressure is a result of collisions of the gas molecules with the wall of the container. And so you can think about a balloon expanding as you put more and more pressure in it. Why does the balloon expand? It's because of there are more collisions with the walls of the balloon. And decreasing volume increases the frequency of collisions because they're closer together. And so we've got a piston, and if we contract it, the pressure is going to go up because they're same number of gas molecules but in a smaller volume, and they're going to be more and more collisions between individual gas molecules and with the walls of the container. And so pressure increases, collision frequency increases. So let's talk a little bit about molecular speed. And when we talk about the concept of the root mean square speed, the U subscript RMS for root mean square. And that's the speed of a molecule with the average kinetic energy, is the speed of the molecule with the average kinetic energy in a gas sample. And so U sub RMS is equal to square root of 3 times R times T divided by M, where R is the ideal gas constant. In this instance, it's 8.314 joules over Kelvin over moles. The ideal gas constant, as we go through this chapter, can have varying numbers and units associated with it. They're all equal to one another, but as you change the units, we wind up changing what the magnitude of the number that goes with it. So different instances, we're going to use different values for the ideal gas constant, so you'll have to be alert for that. T is the absolute temperature in Kelvin. That's really important. And M is going to be the molar mass in grams per mole. So the root mean square velocity, we can sort of think of that, quote-unquote average velocity, is square root of 3 times RT over M. So what does this mean? It means that the RMS velocity is directly proportional to the temperature, because temperature is in the numerator on the other side of that equal sign. But it's inversely proportional to the square root of the mass, the molar mass. So the higher the temperature in the numerator, the greater the RMS velocity. The higher the mass, the slower the gas molecules will be moving. The greater the mass, the smaller, because the smaller the RMS velocity would be, because now you've got a bigger number in the denominator. So here's our equation again. And so what does this, let's see graphically what this means. So let's take just the molecular nitrogen as a gas, and look at what happens as we increase the temperature. Now the area under these curves are all the same, because we have the same number of molecules in each, total number. And so the x-axis is molecular speed, meters per second, and the y-axis, the vertical axis, is the number of molecules. And so as we go from 100 Kelvin to 300 to 700 Kelvin, the curves flatten out, and the maximum, which you could think of as the average statistically, it's going to be the RMS average, that's increasing. So at 100 Kelvin for molecular nitrogen, its RMS velocity is what? 200 meters per second. At 300 Kelvin, it's closer to 400 meters per second. And at 700 Kelvin, it's like 650, 700 meters per second. And so as the temperature goes up, the RMS velocity goes up. Now let's look at the effective mass. And so here we're at constant temperature for all three of these gases. We're at 300 Kelvin. So we've got molecular chlorine, molecular nitrogen, and helium. Chlorine has a mass of 70.9 grams per mole. Diatomic nitrogen, 28.02 grams per mole. And helium, 4.003 grams per mole. So we're at the same temperature. X-axis is still velocity, meters per second. Y-axis is still the number of molecules. And so chlorine's the heaviest. And since mass is in the denominator, that means it's going to be moving the slowest. Helium's the lightest, so it's going to be moving the fastest. And so that's what that plot shows us. Let's talk about two different processes that are sort of similar. And we're going to wind up with a result that will be common to both of them in just a moment. So diffusion is the mixing of gases, and it's the result of the random motion and frequent collision of gases. So diffusion is the mixing of gases. And so this picture, we got two flasks with a valve in between, a stopcock. Purple molecules on the left, yellow molecules, or gas particles on the right. And we open the valve, and now they can mix back and forth. Since they're going to be at the same temperature, which one is going to move faster? It's going to be the lighter molecule, because RMS velocity is inversely proportional to the molar mass. That's diffusion. Effusion is the escape of gas molecules from a container to a region of vacuum, or at least lots lower pressure. And so here we've got a gas, we've got a small hole that the gas molecules can escape or fuse through into what was originally a vacuum. It's certainly going to be a region of lower pressure as the number of particles speeds up. And so diffusion and effusion give rise to something that's known as Graham's law, which we're going in it, is the RMS velocity of two gases is inversely proportional to the square root of their masses. So the lighter molecules will travel the fastest. So how did we wind up with that? So here's the RMS velocity equation for molecule 1 divided by molecule 2. The 3's cancel, the gas constants cancel, the temperatures cancel. And so we're going to wind up with the RMS velocity of compound 1 divided by the RMS velocity of compound 2 is equal to the square root of the molar mass of compound 2 divided by the molar mass of compound 1. They're inversely related. The bottom line is the smaller molecules, gas molecules, travel the fastest.